GCE Advanced Level Chemistry Practical Series Experiment number 1, demonstrating the properties of cathode rays. The aim of this experiment is to provide the necessary skills and knowledge to identify different electrical components of the cathode ray and how to handle the electrical circuitry of cathode ray tube, and to understand how cathode rays behave under different conditions. So we are going to observe the different properties of cathode rays by taking the cathode ray tubes and observing how they deflect in an electrical field and a magnetic field, and when we try to send cathode rays through an opaque object, how they behave and how it would act when we direct the cathode rays towards a pedal wheel. So now let's move on to identifying the equipment we will be using for this experiment. Now students, let's identify the equipment we will be using for this experiment. We have our induction coil. This is a voltage amplifier. So this device will allow you to amplify the voltage that you get from our normal electrical system. We normally receive about 230 volts from the main plug, and this will be able to amplify it to between 10,000 and 15,000 volts. And we have a knob over here to turn it on, off, and regulate the voltage. And there is another knob over here that will allow us to invert the potential difference between these two electrodes. We have wires to connect these electrodes to our cathode ray tube. We have a magnet. We will be using all of these cathode ray tubes. Each of these is a cathode ray tube. Now students, this specific cathode ray tube or discharge tube, it is normally referred to as a Crookes tube, as it is William Crookes who invented the cathode ray tube. So these cathode ray tubes this specific one is made specifically to observe that the cathode rays are traveling in a straight line. So we have an opaque object here at the right hand corner of this cathode ray tube, which we can fold down and raise up again. So this specific cathode ray tube will mainly be used to observe that the cathode rays that is produced here are traveling in a straight line, and it will cast a shadow at the back of this cathode ray. Apart from this cathode ray, we will be using a different cathode ray here that we have here. This specific cathode ray comes with a pedal wheel, a wheel with pedals attached to it. You can see it easily travels along the rails that is provided to this pedal wheel. And this specific cathode ray tube is going to be used to show that the cathode ray or stream of particles produced when it comes to producing a cathode ray has kinetic energy. So we are trying to show that the cathode ray particles, or the stream of cathode ray particles, has kinetic energy with the use of this specific cathode ray tube. Then we have, students, another cathode ray that we have over here. This is used mainly to observe the path of the cathode rays produced. So at the back of this cathode ray, at an angle, you can see there is a white color plate. So this white color plate is coated with a fluorescent material like zinc sulfide, and when our cathode rays are produced from this electrode on the right hand side, a stream of cathode rays will be going towards the left hand electrode. So as cathode rays come into contact with this fluorescent material, you can actually observe the cathode rays as they illuminate a specific path along this fluorescent panel that you see over here. So we can detect the path of the cathode rays that are produced here. Cathode rays are invisible to the eye. So with the use of this fluorescent panel set up inside the cathode ray tube at an angle, we will be able to observe the path of the cathode rays. With that, we have identified the different cathode ray tubes and other equipment and circuitry we will be using for this experiment. Let's move on and conduct this experiment. Let's take a look at this induction coil. Has a few moving parts. We have here two electrodes with pointy needle-like electrodes pointing out, and we have two knobs over here. As I introduced before, what we have here is a knob to turn on and off the device, as well as to increase or reduce the voltage that this device produces. And this particular knob on the right hand side is capable of changing the charge of each of these electrodes. The negatively charged electrode is referred to as the cathode, and the positively charged electrode over here is referred to as the anode. And the cathode and the anode's positions can be switched with this device, with this knob. If you turn this knob, the cathode and the anode will be switched. If earlier this was the cathode, after turning the knob, our electrode on the right hand side will turn to be the cathode. Now students, when you are handling a device such as this, you have to be very careful, because this device is capable of taking in 230 volts that is provided by our grid, and it is capable of converting it into over 10,000 volts. So we can go up to between 10,000 to 15,000 volts with the use of such device. So as you increase the voltage, there is a high risk. If you mishandle it, you can get electrocuted, which is not a desirable outcome. So students, please make sure that you are very careful around a device such as this. And as you turn on the device, make sure when you turn on the device that this knob is set to the off position. And then when you turn it clockwise, you will be increasing the voltage between these two electrodes. When you keep increasing the voltage between these two electrodes, at one point there will be a really high voltage which will allow the electrons from the cathode to jump towards the anode. So this will only happen when you increase the voltage to a significantly higher number. So when there's a really large potential difference between the two electrodes, at that point electrons can jump from the cathode towards the anode, creating a spark. So at that point, where we observed sparks being generated between these two electrodes, you will be able to come to the conclusion that there is a significantly high voltage difference or potential difference between the two electrodes. Now let's turn on the device. We have the knob over here at the off position. Now what we are going to do is we are going to slowly increase the voltage between these two electrodes, and at one point when the voltage is high enough, or when the potential difference between the two electrodes are high enough, you are going to observe sparks being generated or electrons jumping from one electrode to the other. So you can observe here from the left hand side electrode, sparks are generated and it is received by the electrode from the right hand side. So the left hand side electrode is our cathode and the right hand side electrode is our anode. So now students, we have identified what this particular device does. We know that it is capable of amplifying the voltage. We know that it is converting the alternating current that it receives into direct current, which is actually a major important point of this device, because when you are trying to conduct the cathode ray experiment, it is very crucial to have a direct current, and this device is capable of converting the alternating current that you receive from the electrical grid into a direct current. So this mainly is capable of doing three things. It can amplify the voltage from around 230 volts that it receives, and it can amplify it all the way between 10,000 to 15,000 volts, and it can convert an alternating current into a direct current. And apart from that, with the use of this knob, you can switch the cathode and the anode of this device. So these are the three main things that this device is capable of doing. Now, let's move on to the cathode ray tube. Now students, what we have in front of us is a cathode ray tube. So a cathode ray tube is used to observe the cathode rays or the rays emitted by the cathode. So in this particular tube that we have over here, we have a gas at low pressure, and usually it is hydrogen gas that we have inside the cathode ray tubes. So we have hydrogen gas at a low pressure here inside this tube. So inside this tube we have a gas at a low pressure, and we have a cathode and an anode inside this cathode ray tube. And the gas that is at a low pressure over here is going to come into contact with the cathode and start producing cathode rays. And in the theory part of this practical, I would have mentioned how the cathode rays are produced. Now, if you have hydrogen gas inside this cathode ray tube, when we provide a high voltage or high potential difference between the cathode and the anode of this cathode ray tube, the cathode will heat up a little bit. So the gas molecules, when they come into contact with the cathode, first they will turn into atoms, and afterwards, students, when these atoms collide with the cathode, electrons will jump out of the cathode, because cathode is going to be saturated with negative charge, or cathode is going to have a high negative charge. And as atoms come and collide with the cathode, electrons will be repelled from the atom. So atom's outer surface, or we have new electrons surrounding the nucleus. So the outer surface of the atom is going to consist of electrons. So when those atoms come into contact with this cathode, which is now having a really high negative charge, when these atoms come into contact with the anode, electrons from the atom will be ejected away from that. And this removal of electrons, or electrons, will be ejected perpendicular to the cathode plate. So the electrons that are removed will be moving in a straight line perpendicular to the cathode plate. So this is something that we have learned in the theory part of this experiment. I thought of reminding the same to you before we start this part of our experiment. So to test that the cathode rays are moving in a straight line, students, we have this particular design of cathode ray tube, and this particular cathode ray tube has an opaque object inside the cathode ray tube which can be raised like this or can be lowered like this. So we will first connect this cathode ray tube into our induction coil, and we will adjust the induction coil to provide this cathode ray tube with a high voltage. And after providing a high voltage, you will observe that the back end of this cathode ray tube will start to glow with a nice green color glow. And this will indicate the cathode rays are produced and they are traveling towards the back of the cathode ray tube and illuminating the back of the cathode ray tube as the cathode rays collide with the glass that we have over here. And as I mentioned how the cathode rays are produced, we know the cathode rays are going in a straight line. When atoms come into contact with the cathode that is now negatively charged, when the atoms come into contact with the cathode, atoms will lose electrons. Their electrons will be ejected from the atom perpendicular to the cathode plate, and those electrons will travel in a straight line and will go and knock the back end of this cathode ray tube, creating a green glow at the back of the cathode ray tube. So if you want to observe that these cathode rays are traveling in a straight line, we can raise this opaque metal object. So as the cathode rays are traveling in a straight line, if they are in fact traveling in a straight line, they will create a shadow in the shape of this opaque object. So we have a cross here. So the shadow that gets formed at the back of the cathode ray tube should look like a cross. So since you know the theory revolving around cathode ray tubes now, let's move on to the actual experiment and conduct it to see whether we get the expected observation. Students, what we have in front of us is a cathode ray tube. This is also known as a Crookes tube because this cathode ray tube was invented by Sir William Crookes, who is a physicist and a chemist who was conducting experiments to see if gases can conduct electricity. So in his attempts to experiment with gases, he created this cathode ray tube, and what he was observing was when you provide a really high voltage between the cathode and the anode of a tube like this, which is filled with gases at low temperature, he observed the formation of invisible radiation or stream of invisible particles traveling from the cathode to the anode. And these particles were formed at the cathode, so he named these particles cathode rays. And since then, since this was the device that was used to observe these invisible radiation or invisible particles that are traveling from the cathode to the anode, since this was the device that was used to observe these particles, this device was named the cathode ray tube. Since William Crookes or Sir William Crookes is the one who invented this device, this is also sometimes known as Crookes tube. So students, what happened here is that you have a glass tube that is sealed off. Inside this glass tube, students, you have a gas at a very low pressure. So this particular sealed off glass tube contains a gas at very low pressure, and we have our cathode here and we have the anode here. So if you look at this device, also have a cathode which is negatively charged and an anode over here on the right hand side which is positively charged. So if you connect the cathode of the oscillator to the cathode of the cathode ray tube, and the anode of the oscillator to the anode of the cathode ray tube, and close the circuit, you will be observing the formation of invisible radiation, or a stream of particles that are going from cathode to the anode. And this will happen only at really high voltages. So we will have to increase the voltage with the use of this device. So as you increase the voltage at one point, you will observe invisible radiation moving from the cathode to the anode. Now, I keep telling you that there is a stream of particles or invisible radiation moving from cathode to the anode. So if it is invisible, how are we going to observe it? How do we know that this is getting formed? As these radiation or particles move from cathode to the anode, it collides with the gases that we have over here at low pressure. And as these particles come into contact with this gas, it allows the gas to glow. So you will be seeing a green color glow over here when it comes to this cathode rays being formed. This will indicate the formation of cathode rays. And to sometimes observe these cathode rays better, we will sometimes use fluorescent materials such as zinc sulfide. So if you move on to the next steps of our experiment, you will observe that we are using a fluorescent screen that will detect the cathode rays that are produced from the cathode. For the time being, you will observe when you connect this cathode ray to this device, and when we start forming cathode rays, you will observe cathode rays through the glow of the gas that is found inside this tube. So now let's connect this cathode ray to this device, and we'll start the machine and we'll observe the formation of cathode rays. We have two wires with crocodile clips, which we will connect to our cathode here, and we will connect the other end to the cathode here in the cathode ray tube. And then we have another wire that we can connect to our anode, and we will connect the other end of that wire to the anode of the cathode ray tube. Over here, the cathode ray tube that we have also contain a gas inside of it at a very low pressure, and we have a cathode on the right hand side. What we see over here is the cathode of the cathode ray tube, and at the bottom you can see another electrode that would be our anode. And as he was conducting this experiment, he noticed a ray of invisible radiation was formed from the cathode and was moving in a straight line towards the anode. Later on, it was discovered that this ray or invisible ray, or ray of a stream of particles that were produced from the cathode, were actually electrons. So now we know the cathode rays that we observe over here are electrons. But at that point, when he initially discovered them, he didn't know whether they were electrons or not. So the ray of these invisible particles that are formed over here were traveling seemingly in a straight line. And since this stream of particles or invisible radiation was formed from the cathode, these rays were named cathode rays. And since we use this device to observe these rays, this device was named cathode ray tube. So now, students, we have connected this cathode ray tube into this device. The cathode of the cathode ray tube is connected to the cathode, or the negatively charged end, and the positively charged end of the power supply, or the anode, is connected to the anode of our cathode ray tube. Now, we are going to turn this device on and we are going to start providing a bit of a high voltage to this cathode ray tube. And you can see as I start providing a high voltage, there's a stream of invisible radiation traveling from the cathode straight towards the anode. Although the anode is over here, since the rays are traveling in a straight line, you can see the back end of this cathode ray is starting to glow. Now students, although the particles that are emitted by the cathode are invisible, they are capable of colliding with the gas particles inside the cathode ray tube and allowing them to glow. Or else, if there is a fluorescent material that they come into contact with, they will allow this fluorescent material also to glow. Later on, we'll be using a different cathode ray which is containing a fluorescent screen to identify the path of the cathode ray tube, to identify the path of cathode rays, as when cathode rays come into contact with a fluorescent material, it will allow the fluorescent material to illuminate. Over here at the back end of this cathode ray tube, you can see it is starting to glow. This is because cathode rays have been produced, and since they have traveled in a straight line, you can see the back end of this cathode ray is glowing. Now, to make sure that we understand that the cathode rays are actually traveling in a straight line, what we can do is place an opaque object, an object that will not allow cathode rays to pass through, between the cathode and the back end of the cathode ray tube. So students, to observe that these cathode rays are traveling in a straight line, we can place an opaque object between the cathode and the back end of this cathode ray tube. And we have a metal cross lowered inside this cathode ray tube. We can raise it up and place it right in between the cathode and the back end of the cathode ray tube. So if the cathode rays are traveling in a straight line, it should cast a shadow at the back end of this cathode ray tube in the shape of this cross. So let's turn off the device first. Let's turn off the device. And let's raise this cross into an upright position. Now we have raised the cross into an upright position, as you can see over here. Now let's turn on the device and let's form some cathode rays and see whether it will cast a shadow in the shape of this cross. Now students, if you observe closely, you will be able to see a darker region, or in other words, a shadow cast on the back of this cathode ray tube due to cathode rays traveling in a straight line. As cathode rays travel in a straight line, they come into contact with this opaque object or object that will not allow the cathode rays to pass through. So therefore, a shadow in the shape of this object is casted towards the back of the cathode ray tube. You can very clearly observe the formation of a cross or formation of a shadow in the shape of a cross at the back of our cathode ray tube. Now students, we can very clearly see the shadow that is observed here when we place an opaque object along the path of our cathode rays that is produced in this cathode ray tube. So let's turn off the device. So why did we observe a shadow in the shape of this cross? The reason for observing a shadow that is having the exact shape of this cross is because the cathode rays that are produced at the cathode over here traveled in a straight line. So we can be certain with this experiment, we can be certain that cathode rays travel in a straight line. So with this experiment, actually J.J. Thomson, who carried out further experiments into our cathode rays, actually conducted this experiment and discovered the fact that cathode rays are traveling in a straight line. These invisible particles or invisible radiation that is produced from the cathode was actually traveling in a straight line. And that was proven by placing this opaque object along the path of the cathode rays, and noticed that it casts a shadow in the exact shape of the object placed in front of the cathode rays. Now let's move on to our next experiment. Students, we have in front of us a cathode ray tube with a paddle wheel inside of the tube. So we can see here inside this cathode ray tube we have a set of rails made out of glass, and on those rails we have a very light metal paddle wheel. So as you turn on this cathode ray tube, as cathode rays are being formed and when they are trying to travel from the cathode towards the anode, along their path you have the paddle wheel. So the cathode rays will come into contact with the pedals of the paddle wheel, and we are going to observe that the cathode ray particles, or whatever the particles that are emitted by the cathode, actually has kinetic energy. We are going to observe that the cathode rays have kinetic energy by observing that this paddle wheel are starting to move when we turn on the cathode ray tube. As the cathode rays are formed when they travel from the cathode to the anode, we are going to observe even the paddle wheel is going to start spinning and travel from the cathode to the anode. And if you switch the cathode and the anode by turning this knob that we have over here, we are going to observe the wheel will also start traveling in the opposite direction again from the cathode to the anode. So it will go from cathode to the anode along with the cathode rays. So this indicates that the particles that are emitted by the cathode had momentum or kinetic energy. So the particles that are emitted by the cathode actually had momentum or kinetic energy. So for example, if my right hand side, this particular electrode, let's say if that is our cathode, as cathode rays get formed from this side of the cathode ray tube, where they will try to travel towards the anode. And you can see the paddle wheel is over here. So when the cathode rays are formed from the cathode that we have over here and travel towards the anode, they come into contact with the pedal of the paddle wheel, and as these cathode ray particles hit the pedal will turn and it will start spinning and traveling towards the anode. And if I switch the cathode and the anode, you will see the paddle wheel will start moving in the opposite direction. So as this experiment is conducted, I'm going to keep switching between these two electrodes. I'm going to make sure that one of the electrodes is a cathode, and then later on, after a few seconds, I will switch it so that that becomes the anode and the left hand side electrode becomes the cathode. Now students, I'm going to turn the device on, and at this point the device is set up for this right hand side electrode to be the cathode, and you are going to observe this pedal wheel traveling from the right hand electrode, which is the cathode, towards the anode that is found on the left hand side of this cathode ray tube. So let's turn the device on. You can observe that the pedal wheel moved towards the right hand side. Now if I switch the two electrodes, you are going to observe the pedal wheel is traveling towards the right hand side. As you can see, when it comes onto the end of the track, it gets pushed back, but again it keeps on traveling towards the right hand side. But if I switch each time that it reaches the end of each track, you can see this pedal wheel keeps traveling back and forth. So as it goes from left to the right hand side, the left hand side is the cathode, and when it travels from right to the left hand side is our cathode. Now when I turn it again, you can see left hand side becomes the cathode. Now the right is the cathode. Again the left is the cathode. You can see now I will turn the right hand side to be the cathode. So this is how you can actually observe. This is how you can observe that the particles that are formed in the cathode or at the cathode is actually having some kinetic energy. So now we have come to observe two main things, that the cathode rays that are generated at the cathode are traveling in a straight line. We observed it in the first part of this experiment, and on the second part of this experiment we observed these particles have kinetic energy, or the stream of radiation or stream of invisible particles that are traveling from the cathode to the anode has some kinetic energy or momentum. So that was observed by the fact that this pedal wheel was starting to move from the cathode towards the anode when we produced cathode rays. So students, with that part of our experiment, we can now move on to the next experiment. Now students, we have another type of cathode ray tube over here. Now this specific type of cathode ray tube is used to observe the path of the cathode ray. So you can see there's a metal plate that we have over here, and this is the cathode and this end is the anode. And you can see when the cathode is producing the cathode ray tubes, when the electrons are coming out of the cathode ray tube, according to the process that I mentioned in the previous part of this experiment, when these cathode rays are produced and when they are coming towards the anode, when they are moving in a straight line, they encounter this metal plate that will block the cathode rays. However, there is a slit in the middle of the metal plate that we have over here. Cathode rays cannot travel through such a thick metal plate, so this slit or the opening that we have in the middle will allow the cathode rays to travel through, and this will create a beam of cathode rays. So this cathode ray beam will be traveling in a straight line. As they travel in a straight line, they will come into contact with the metal piece that is placed inside the cathode ray tube at an angle, and this metal piece is coated with zinc sulfide, a fluorescent material. So when the cathode rays come into contact with this fluorescent screen, it illuminates the areas that comes into contact with cathode rays will get illuminated. So the path of the cathode ray will be illuminated with this zinc sulfide fluorescent screen. If you take a look at the top view of this cathode ray tube, you will be able to see that this zinc sulfide screen is placed at an angle so that cathode rays, or the beam of the cathode ray that is taken into this middle section of the cathode ray tube, comes into contact with this zinc sulfide plate that we have inside the cathode ray tube. So students, this particular cathode ray tube is mainly used to observe the behavior of the cathode ray when subjected to a magnetic field and electric field. Now, before we start turning on the induction coil and observing the path of the cathode ray, you should know the cathode rays are traveling in a straight line. We have proven it. Even in this particular cathode ray, that will be very clearly observed. Apart from that, we know when subjected to a magnetic field, cathode rays will move perpendicular to the magnetic field. Cathode rays will not get attracted to either the north pole or the south pole of a magnetic field. Instead, cathode rays will move or will get deviated perpendicular to the magnetic field. If you have a magnetic field above and below, as cathode rays pass through the magnetic field, they will move in a perpendicular plane to the magnetic field and will get deviated due to the presence of the magnetic field. So we will observe that over here. And apart from that, we are going to observe what happens if you bring a negatively charged copper plate close to this cathode ray that we observe over here. So cathode rays are basically moving negatively charged particles. So, or we can say cathode rays are a moving beam of electrons. And as you bring a negatively charged copper plate, you would see that the cathode ray is deviating away from the negatively charged copper plate. So this indicates the stream of cathode rays or stream of particles found in cathode rays are negatively charged. Or in other fact, we do get the confirmation that the cathode rays are consisting of electrons, and electrons are negatively charged, so therefore they will get deviated away from the negatively charged copper plate that we bring close to our cathode ray over here. So students, let's move on to that observation. So first, let's observe how the cathode ray behaves in the presence of a magnetic field. We'll connect the cathode and the anode to the relevant electrodes, and then we will turn on our induction coil, and you can observe the cathode rays are traveling in a straight line. You can observe very clearly that the fluorescent screen is getting illuminated only in a straight line. So if you bring a magnet to it, a magnet has a north pole and a south pole, you will observe how the cathode ray changes its path based on how we introduce the magnet towards the cathode ray that we have over here. So the cathode rays are traveling like this. So if we bring the magnet at this angle, the magnetic field will be going in a straight line. So when I bring the magnetic field, you will see how the cathode rays are moving. So the magnetic field will be pointing towards the camera, and cathode rays are traveling in a straight line, right? So at that point, you can see how the cathode rays are not getting attracted towards the north pole. Instead, it is getting deviated in a perpendicular plane to the magnetic field. You can very clearly see this observation. Now, if I change the direction of the magnetic field, you will observe how the cathode ray behaves when we direct the south pole of a magnet towards the cathode ray. So the magnetic field is now forcing the cathode ray to deviate at a perpendicular angle to the magnetic field. Now, you can observe the same observation when we bring the magnet from the top. But now keep in mind, students, the cathode ray is traveling from my right hand side to the left hand side in a straight line. So when I introduce a magnetic field that is pointing downwards, the cathode ray will try to move at a perpendicular plane to the magnetic field. The perpendicular plane to the magnetic field at that point would be this plane that I'm indicating right now. So the cathode rays will try to turn inwards towards me. At that point, you will see that the cathode ray beam is disappearing. Cathode ray beam is disappearing because as it is getting deviated towards my direction, as cathode rays move towards my direction, you can see the cathode ray beam is disappearing when I bring the north pole towards the cathode ray. So the magnetic field is pointing downwards now. So at that point, cathode ray is trying to move at a perpendicular angle towards my direction. If I direct the south pole, cathode rays are now moving towards the camera or towards you, and you will observe the cathode ray beam becoming wider and trying to deviate at a perpendicular angle towards you. So it is not disappearing. Instead, towards the end of the fluorescent screen, you can see the cathode ray tube getting wider. Towards the end of the cathode ray, you can see the cathode ray getting wider. This indicates that cathode rays behave as charged particles behave in a magnetic field. In a magnetic field, as you may know, charged particles also get deviated in the presence of a magnetic field. The same way, cathode rays get deflected in a magnetic field. So let's observe one more time what happens when we bring the magnetic field in this particular angle towards the cathode ray. So you can very clearly observe how the cathode ray behaves when a magnetic field is applied to it. So when the magnetic field is applied in this particular direction, you can see the cathode ray is trying to move in a perpendicular plane to the magnetic field. The perpendicular plane to the magnetic field at this point is the plane that I'm indicating right now. So the cathode rays are trying to move in this plane. So cathode rays will come, get subjected to the magnetic field, and are now trying to move up. And then cathode rays will come down when the south pole is directed towards the cathode ray tube, like so. Now, students, after making that observation, we can move on to the next experiment, where we bring a charged or negatively charged copper plate towards this cathode ray tube. So let's move on to that experiment. Now, students, we are going to observe how the cathode ray behaves in the presence of an electric field. So we have here a negatively charged copper plate, and as we bring this negatively charged copper plate towards this cathode ray, you will observe how the cathode ray deviates. So cathode ray, when we turn on this cathode ray tube, you will observe the cathode ray is traveling in a straight line. When we bring down this negatively charged copper plate towards the cathode ray will get deflected away from this negatively charged copper plate. So this indicates that the cathode ray consists of a stream of particles that are negatively charged. We learned that cathode rays show particle properties, and cathode rays are traveling in a straight line. And now with this experiment, you are going to observe the fact that cathode rays are in fact negatively charged stream of particles. So let's turn on the cathode ray tube. Now you can see the cathode ray is traveling in a straight line, but as we bring this negatively charged copper plate, you will observe that it deviates away from the copper plate. As we remove it, it returns back to its original straight line path. However, if you bring this copper plate close to the cathode ray, we can observe that the cathode ray gets deflected away from the copper plate. As you bring it close to, you will observe, as we bring the copper plate close to the cathode ray gets deflected away from the copper plate. So students, you can very clearly see the cathode ray is no longer traveling in a straight line. This indicates that the cathode ray gets deflected away from this negatively charged copper plate, indicating that the cathode ray particles are negatively charged. In fact, we know that cathode ray is consisting of electrons, and electrons are negatively charged, and it will get repelled from this negatively charged copper plate. So that is why you can see the cathode ray is moving away from this negatively charged copper plate. Now students, this is the observation that I want you to make about how the cathode ray gets deflected away from the copper plate that is negatively charged. And after making this observation, we can now move on out of this part of our experiment. Now students, let's take a look at the summary of today's experiment. So in our experiment, we first started giving an introduction to this device. So we learned that this device is capable of doing mainly three things. It is capable of amplifying our voltage. So the input voltage would be around 230 volts, but it can be elevated all the way up to 10,000 or to 15,000 volts. And we learned that this device is capable of converting an alternating current into a direct current. Apart from that, with the use of a knob or a switch that we have over here, we were capable of switching the cathode and the anode between these two electrodes. After doing the introduction to this device, we moved on to our cathode rays. So all three of these tubes that I have in front of me are cathode rays that are used to show different behaviors of our cathode rays. The first tube that we have over here has a erasable opaque object inside the cathode tube or cathode ray tube. So this particular cathode ray was used to show that cathode rays are traveling in a straight line. We saw that when we connected the cathode of this cathode ray tube to the cathode of this device, we saw when cathode rays were formed, they were traveling in a straight line and later on casted a black color shadow in the exact same shape as the object that we have placed in front of our cathode rays. So this shadow that was casted in the shape of this exact same object indicated that the cathode rays were traveling in a straight line. Then we moved on to the second cathode ray tube. In this specific cathode ray tube, we observed that there is a pedal wheel inside the tube. So we use this second cathode ray tube to show that the cathode rays or the stream of particles that are found in the cathode rays have kinetic energy. So as the cathode rays gets formed from the cathode and moves towards the anode, we observed that this pedal wheel also started moving from the cathode towards the anode. This indicated that the cathode ray particles that were hitting or coming into contact with the pedal wheel allowed the pedal wheel to turn and move towards the anode. So kinetic energy that was found in the cathode ray particles were transferred into our pedal wheel over here, and the pedal wheel started moving exactly in the same direction as cathode rays did. So this particular experiment was conducted to show that the cathode rays are not simply a type of radiation without a mass or kinetic energy. We observed that the cathode rays are a stream of particles that had kinetic energy and momentum. So after observing the fact that cathode rays had kinetic energy in it, we moved on to the next experiment where we used this cathode ray tube with a fluorescent screen placed within the cathode ray tube at an angle, or we can say it is slanted, so that as the cathode rays travel from anode or cathode towards the anode, the slanted fluorescent screen actually comes into contact with the cathode rays, and since this fluorescent screen is coated with a fluorescent material like zinc sulfide, when the cathode ray comes into contact with this fluorescent material, you will see the fluorescent screen will get illuminated along the path of the cathode ray. So the cathode ray's path will be illuminated so that we can observe it. So when it comes to this particular device, we used it to observe how the path of the cathode ray got deflected in the presence of a magnetic field and in the presence of an electric field. In the presence of a magnetic field, we observe the cathode rays are getting deflected in the exact same manner how negatively charged particles get deflected. If negatively charged particles get deflected in a specific manner in the presence of a magnetic field, in the exact same way, you will observe the cathode rays are also going to get deflected. And then when we brought an electric field close to our cathode ray over here, we observed when a negative electrode was brought close to the cathode ray got deflected away from the negative electrode. Cathode ray got deflected away from the negative electrode because the cathode rays were negatively charged. So students, this final test confirmed the fact that cathode rays are having a charge, and that charge is negative charge. So later on, with further experiments, J.J. Thomson identified that these cathode rays that we observe here are actually electrons. After J.J. Thomson came across these observations, he further conducted experiments changing the type of gas inside these cathode ray tubes, and he observed the same observations. He realized the particles that are getting formed at the cathode did not depend on the type of the gas that was present or on the type of the metal used for the cathode. Then later on, he discovered that these particles that are emitted by the cathode are in fact electrons. With that, we can conclude today's experiment. Let's move on to questions and other important theory parts revolving around this experiment.